lecture. Welcome to the fourth lecture on nonlinear optics. Let me quickly repeat a little bit the things that we did last time. Namely, we were still looking at a very simple way of approaching nonlinear optics, namely just with, to be serious, with trigonometry. And we looked for the second order processes first, and we had things like second harmonic generation, like difference frequency generation, sum frequency generation, and so on and so forth. And then we looked for third order processes, and we did pretty much the same thing. We looked first for the degenerate case, which means that all the frequencies, all the input frequencies are the same. And no surprise, what we got was third harmonic generation. But these trigonometric identities, they delivered also a term that oscillates, so where the polarization oscillates with the fundamental frequency, so with omega. And then we said, oh, wait a minute. In chapter 1, we discussed the origin of the refractive index, and we said that the refractive index is basically due to the polarization that oscillates, that is excited by the incident field, and that oscillates, of course, in the linear case also with omega. And now we have the same thing, just it's a nonlinear polarization, but it still oscillates with the fundamental frequency. And so we said, well, this should lead to a change in the refractive index. And we'll see that this is actually the case. And we also already looked at a few examples, and I just want to repeat them with a few nice photos. So what you have here is on the left-hand side, the picture, the photo that I showed already. So this is from this building where, well, 17 years ago or so, the Yeti laser beam was shot into the air, and then due to self-focusing, but also a number of other complicated effects, you create a channel of light, a so-called filament. Right? What we have here is that, well, this is this formula here where the index of refraction is modified. But what we use here is its spatial dependence, because, well, virtually every laser beam has a spatial dependence. Typically, the beam has more intensity on the beam axis, but actually this is not always the case. You can also produce other cases of beams. But if you have such a beam, then you immediately deduce from Fermat's principle that you should get something like self-focusing. Yeah? What we also can do, in case we have a short pulse, actually also there is a short pulse. If you have a short pulse, then you have a time-dependent change in the refractive index. And this leads to self-phase modulation. We'll come to that in a few chapters from now, so actually next year or so. Yeah? And the interesting and the exciting thing here is that you produce new colors. So this is shown here. So the laser sits somewhere here and produces, I guess, near infrared laser pulses that are apparently already sufficiently broad that you see the blue wing of the red infrared. So this is what you see here. And now this travels through a special fiber, and the fiber is made such that the pulses remain short. Normally, if you propagate an ultra-short pulse through a fiber, it gets longer and longer and longer. And then, of course, the derivative of this here, which produces self-phase modulation, becomes too small. But this fiber here is made in a particular way such that it has no, we say, second-order dispersion for those of you who already had some exposure to the optics of ultra-short pulses. So these pulses remain short, and therefore this process of self-phase modulation and a few other things, they are ongoing throughout this fiber, and you see that it changes from red to orange and then to yellow, finally to green, and eventually to blue. Yeah, so you change, and actually if you look at with a spectrometer at the spectrum, then you see so all the colors of the rainbow and more, right? So it goes into the infrared on the on the left-hand side to the ultraviolet, only limited by the transmission of the fiber. Yeah, spectacular effects and also very important effects. So this is this is a glimpse of the effects that we can watch when we use this degenerate case that I just described. But in general, we have of course three different colors, and a fourth color will come out, and therefore these processes are called typically four-wave mixing. And now I can do the same thing that I did for second-order nonlinearities. Yeah? So I can look at the general case of third-order processes, and what you see is that I would of course write down three different frequencies, yeah, plus their complex conjugates, and then if I would take the cube of that. Yeah, so remember, for second-order processes, we had two colors, and we took the square of it. Now we have three terms in general, and we take the cube. So you can imagine you will get a lot of terms. And actually, if you count them, then these are, in general, 44 terms. Yeah, so 6 terms here, another 4 terms here, another 12 terms here, and then you have to take the negative of all that. Yeah, 22 times 2 is then 44 different terms, and each of them produces a polarization. And well, if you look at all the polarizations, it really doesn't make any sense to write them down. So you find them in the script, and I have noted them here. You can do a little bit of analysis, say, on these factors here. For example, that you have here the factor 6. This corresponds to the fact that there are 6 permutations of these 3 indices, right? Whereas if for this situation there are just 3 of them, and a few other things that you find in the script. With this, I would actually like to go to the next subchapter before we come to the main topic of this lecture. We want to start to derive the coupled wave equations, and I said that this is core material of this course. But before we do that, we want to classify nonlinearities in a little bit different way, namely according to what's called parametric and non-parametric processes. Don't ask me where this term comes from. I have an idea, but I'm actually not sure whether this is right. At least I can define it, what is meant with parametric and non-parametric processes. So we speak of parametric processes if, besides the ground state, so here you have a simplified level scheme, so we have a ground state, and besides this ground state, there are only virtual levels involved. This defines parametric processes. In other words, you don't really absorb energy in order to transfer the population, say, from the ground state to an excited state. Yeah? So what you do is that you kind of use the energy time uncertainty, and you say, I can borrow for a short time I can borrow some energy, so I can absorb some photons, and then within this time they need, of course, to go back to the ground state in order to fulfill energy conservation. Yeah, so we absorb virtually 3 photons in order to emit 1 by the system. So let's write that up. I kill the echo here. So first thing to note is that we speak of parametric processes when only virtual levels are involved, besides the ground state, of course. Yeah, so population can be removed. Population can be removed from the ground state. Yeah, so I write it as G in this bracket notation for a time period that we call delta t. That is allowed by the uncertainty principle. By the uncertainty principle, so meaning the delta t is smaller than approximately h bar divided by delta E. Yeah, and you see here in this sketch what delta E is. So this is the energy difference between the ground state and this upper virtual level. Yeah, and you can also say it in a different way. Parametric processes don't change the quantum state of the material. Parametric processes do not change the quantum state of the material. In contrast to this, we have, of course, non-parametric processes, and there the quantum state is changed. So what it means typically is that photons are absorbed. Maybe photons of one color are absorbed and photons of other colors are emitted. We'll come to that. Yep. So for non-parametric processes, population is removed from the ground state, from G to an excited state. Yeah, this typically means that incident radiation is absorbed. Yeah? So when we don't absorb, then we can describe the susceptibility just by real numbers. Yeah? And this is my next point here. Yeah? So it's just a quick remark. Yeah? What follows is that parametric processes can always be described by a real susceptibility. Yeah, so no absorption, of course. Yeah, and you realize immediately there is not really any material that does not absorb in a strict sense. Yeah, so parametric processes, this is an idealization, of course. Yeah, and this means, as there is always some absorption, parametric processes are an idealization. Okay, let's discuss a few examples. Yeah? So the most trivial example of a parametric process is, can you just think of a few, perhaps in yeah, so second harmonic generation, that would be one. So here SBDC somebody is writing. I'm not quite sure. I think this is a typo, right? But actually, I would know even simpler parametric processes. For example, just the refractive index, or diffraction, or Rayleigh scattering, or Mie scattering. Yeah, these are parametric processes in linear optics. Yeah? So this would be the a trivial example, or trivial examples. Yeah, so the ordinary index of refraction yes, a parametric does not necessarily mean that we are talking about nonlinear optics. So index of refraction, diffraction I said, then scattering, yeah, Rayleigh scattering, and Mie scattering. Yeah, so scattering, elastic scattering, scattering where the photon energy is not changed. So these are trivial examples for parametric processes. And then for non-parametric processes, yeah, so examples for non-parametric processes, photoluminescence or fluorescence and these things. Photoluminescence would be one example. I have a figure here for that. Oh, yeah. So photoluminescence. So I found these on Wikipedia. I thought that I'm I wanted to give the reference here. Unfortunately, it disappeared. Yeah. Okay. Now the reference is here. So what was done here was that some dyes were solved in water. Actually, a very small amount. So rhodamine 6G, rhodamine B, and other dyes, and they were illuminated with ultraviolet light that you don't see, and then you these fluids, they light up in all kinds of colors, depending on the dye molecule that's in there. So, and now I'm a little bit unhappy with this thing here. So, and the physics of what's going on is the following. So an incident photon would transfer an electron from, well, in a solid state material, it would be the valence band. So here it's the valence shell, and would transfer it into an excited level. And because if you have a complicated molecule, then you have all kinds of vibrational states and so on, right? And what happens is that the electron that is transferred into, say, a high-lying vibrational state quickly decays to the lowest point here, and the same thing happens for the whole, and then it may recombine if you have a direct transition as shown here. So the details are not interesting. Yeah? So you see that this is clearly different from what we discussed when we were talking about parametric processes. So where does this term parametric process come from? Well, as I said, I'm not sure where it comes from, but in mechanics, you have a certain type of driven oscillators that are called actually parametric oscillators. And the simplest example is the child's swing. Yeah, so every child quickly learns how to drive this oscillator, this swing, and it is done by lengthening and shortening the string of the swing. Yeah, so by just bending it a little bit, right? And if this is done with the right phase, then you swing more and more, and well, the length of the string of the swing is a parameter in this differential equation. Because you change this parameter, you can excite this oscillator. Yeah? So they are called parametric oscillators, these systems. And I guess that this term comes from there. And what makes it even more likely, so this statement is that much of nonlinear optics was actually not developed by physicists, but by engineers, by electrical engineers. Because, well, the physicists in the 60s, they were not really, so optics was perhaps not the most exciting topic there. Yeah, so nuclear power and high energy physics were much more exciting at that time. So optics was considered to be something of the 19th century or so. And so physicists gave this part of physics away to the engineers. And the engineers, on the other hand, they just had started to invent all these modern wireless transmission things, radios and so on, and parametric amplifiers do play a role there. Yeah, so they knew about all kinds of frequency mixing. So much of the the physics and the mass of this field was actually developed by electrical engineers. Okay, so but this is just a speculation. Somebody would need to do some history of science on it. Let us look at a few examples of non-parametric processes. You'll see that we'll mostly concern about parametric processes, which, however, does not mean that non-parametric processes are less important. And I'll give a few examples now. So examples for non-parametric processes. Examples for non-parametric processes. I think we need to open the windows quickly. 20 minutes are over. Yeah, I need, so yeah, examples for non-parametric processes. Thank you for reminding me. Then the first example would be saturable absorption. Now, the idea is the following. You have a situation like the one just depicted. Perhaps I included here into this script. So this one here. Yeah. And now imagine that you have, well, a finite number of these molecules, and you shine on them with a really intense laser. Then you might actually bring a substantial fraction of the molecules from the ground state to the excited state. Right? And well, if you take the extreme case, if all of the molecules would be in the excited state, then this molecule can't absorb any longer. Yeah? So in colloquial language, we would say it bleaches out. It becomes transparent. Yeah? And this is what's meant by saturable absorption. I think we have enough fresh air. We don't want to freeze here. So many materials share the property that their absorption coefficients decreases if the laser intensity, yeah, it's typically done, of course, with lasers, if the laser intensity gets very high. Yeah, and for a homogeneously broadened medium. Now, what does this mean, homogeneously broadened medium? Well, let me explain what inhomogeneously broadened medium is. An inhomogeneously broadened medium is when you have different, say, velocity classes of molecules, right? So if you look for the line shape of say a transition in you have a gas, and say you have sodium gas, yeah, and you look for the sodium D line, for the famous sodium D line, this orange line, and you look with a high resolution spectrometer, then you will find there is actually not infinitely sharp line as you would also expect, right? But that this line is broadened, and the broadening of this line is typically due to the Doppler shift. Yeah, so these atoms, they have a fairly high velocity, and therefore you see the light shifted by the Doppler effect in all kinds of because due to the different velocities of these atoms. Now, suppose that you somehow manage to cool them to, say, millikelvin temperature such that their velocity is negligible, right? Then there is still a finite line width that comes just from the lifetime of the excited state. And this then would be the homogeneously broadened line width. So it's very high, yeah, and we can write down a formula for homogeneously broadened transitions. For homogeneously atomic transitions. The time-dependent absorption coefficient, typically you would use a pulse, and then you would excite many molecules to the excited states. So, well, no, I don't mean time-dependent, I mean intensity-dependent. The intensity-dependent, of course. If you have a pulse, then of course both are correlated. The intensity-dependent absorption coefficient can be written as alpha, so that's the absorption coefficient, is equal to some alpha naught, which is the absorption coefficient at low intensities. And then we have 1 plus I, the intensity, divided by the saturation intensity. Yeah? Sounds a little bit trivial, doesn't it? But actually it is not, because this effect is actually at, well, this is actually the starting point of many important technologies. One of them is high resolution or super resolution microscopy, yeah, so where the fluorescence is actually suppressed by this effect. But we also have others that are much older than this effect, namely optical bistability, and I have a view graph on that. Sorry. Yeah, so this is optical bistability. So there the idea is the following. We have a cavity as shown here, yeah, so just two mirrors. And, and this, without the saturable absorber, this would mean that the intensity, the light intensity within this cavity is higher than the input intensity, right? So depends on the finesse of this cavity. Now you put a saturable absorber inside, and then if the intensity is too low here, then it will just block the light, right? And only a small amount of light will come out. So this is what you see here. Yeah, if I increase the intensity here, the input intensity here, then the output intensity will only increase, yeah, rather weak. But now, as you increase the intensity, you start to bleach out this Sutter-Ripple absorber, right? And suddenly it becomes transparent. And therefore, the intensity here jumps up, right? And if you pump more light into it, then you get out even more, as you would expect. But now the interesting thing comes when you go the other direction. So when you go in this direction, right? Then, as I said, the light intensity in this resonator is larger than the input intensity, and so you still bleach it out, right? And therefore, you get kind of this hysteresis behavior. So that's optical bistability, and 30, 40 years ago, this was a very active field of research because people thought that this would be one option to build an optical computer. Because this is a switching behavior, and if you control it in some way, then you can make perhaps an optical transistor. It didn't lead to much, but it has been a very active field. Another very important, a much more important technology as compared to bistability and also as compared to STET microscopy is high-resolution saturation spectroscopy. And here you see one of the most famous laser scientists. This is Ted Hensch, still working at the Max Planck Institute of Quantum Optics. I had the pleasure to visit him a few years ago. Actually, I know him very well, so he's a very nice man and one of the, so a real genius. And one of his first Geniestreich, what's this in English? Yeah, so one of his first major things was the invention, or co-invention actually, of high-resolution spectroscopy. So spectroscopy was all the times limited by inhomogeneous line broadening. So to find the homogeneous line width, say, of the sodium transition, and I think this here is also on the sodium, it's also on the sodium D line. To find the natural line width has been a challenge, right? And now they did the following trick. Yeah? So you use a tunable laser. Of course, for laser spectroscopy, you would use a tunable laser, right? But if you do it in the regular way, then you also just, as you tune the laser through the resonance, so the setup is quite simple. You take a laser, you take your sample, and you put a photodiode behind it. And now you tune your laser through the resonance and record what the photodiode gives, right? And what you would get is, of course, the negative of the line, so you would see the absorption of this line. Yeah? But you would measure the inhomogeneously broadened line, so broad bandwidth. But now, how to get to the natural line width? How to make high-resolution spectroscopy? Well, the trick is the following. You split your tunable laser into two, into a stronger part, which is probably this one here, right? That bleaches the medium, and well, you probe it in the other direction, and now the following happens. Yeah? So you have two counter-propagating beams, and now if you have a molecule that moves to this direction, then for this beam, it is red-shifted, and for the other, it's blue-shifted. Yeah, so both beams don't speak to the same class of atoms, because both have the same frequency. Right? So you bleach, say, those that travel in this direction, but with the other beam, you're in resonance with those who go just the opposite way. Right? only those atoms that have no velocity component in the laser beam axis, they see for both the same frequency, yeah? Because they have no Doppler shift. Yeah? And so one has here Doppler-free spectroscopy, and this was this was a real breakthrough for laser spectroscopy. Well, to be serious, it was the beginning of laser spectroscopy in many ways, because with this technology, laser spectroscopy suddenly had a much higher resolution as compared to all the other technologies, right? And this is true to the present day. With laser spectroscopy, you can get resolutions of 15 digits or something like that. And Ted Hensch is still one of the leading figures in this business. Yeah, and it can be used to determine fundamental constants, and what he is after is looking at possible variations of fundamental constants, and all that is done with laser spectroscopy, and Doppler-free laser spectroscopy was one of the first things there. Okay, well, actually one of the earlier examples that I have shown, namely two-photon excitation, so one of the first nonlinear effects to be discovered by Wolfgang Kaiser and others. This was two-photon excitation, actually, so this was a non-parametric process. Two photons were used in order to transfer population from a ground state to an excited state. Of course, second harmonic generation is a parametric process in contrast. And another very important application of Zetter-Ripple absorption is the generation of ultra-short pulses. In order to generate ultra-short pulses, you need to couple the modes of a laser. Yeah, so first of all, you need to build a laser that has as many modes oscillating at the same time, and then you need to couple them. And a Zetter-Ripple absorber is actually a very obvious way to do that, because suppose you manage to couple them. Yeah, this means at the same time that you have a short pulse, and if you have a short pulse at a given laser energy, then you have an intense pulse. Right? So once you somehow succeed, perhaps even out of the noise, to produce a short pulse that is able to bleach the Zetter-Ripple absorber that you put into the laser cavity, then this laser suddenly would produce short pulses. And what you see here is the machine with which I worked. So this was the first femtosecond laser at the Max Planck Institute of Quantum Optics. And I did my diploma thesis on that, my PhD thesis, and the first half of my habilitation also. And it had, yeah, so this is how it looked, this laser. So these were the femtosecond lasers, the first femtosecond lasers. Yeah? And actually also this institute, Bernd Wilhelmi, they were at least as, yeah, so they were actually ahead of us. Of course, before reunification. Yeah, so this was the laser technology of the 1980s until the titanium sapphire laser replaced them in a matter of a few years. Yeah? It was not very comfortable to work with these lasers. Yeah? So one had a dye jet as an amplifier. This was pumped by an argon ion laser. This is this red thing here behind. Yeah? So an argon ion laser. Yeah, so there was an amplifier dye, rhodamine 6G in this case, right? And there was also an absorber And these mirrors around these absorbers and amplifiers, they were used in order to focus the laser beam into these dye jets, right? And there were high power pumps pumping these two dyes, these two different dyes through the nozzles here and here. Well, and then there was some dispersion compensation, and why this is called colliding mode lock dye laser. So what you see is that it's a ring laser, and you have pulses then counter-propagating. You have two beams counter-propagating, and it was done in such a way that the pulses would collide in the Satellite absorber, right? And therefore, this distance here is about a fourth of the entire length. Yeah, so early technology, but on the other hand, Satellite absorbers for producing short pulses are still common technology to achieve mode locking. Okay, so Satellite absorption. Let's write a few more things here. Yeah, so super resolution microscopy. Yeah, so STET microscopy. Then, as I said, saturation spectroscopy. And finally, mode locking. In Satellite absorbers, or by Satellite absorbers. Well, and then there's another important class of non-parametric processes, and these are Raman. This is Raman scattering. Yeah, so another class of Satellite, no, not of Satellite, of non-parametric processes. Raman scattering. And there are all kinds of Raman scatterings. Yeah, so there are spontaneous processes and also coherent processes, which is then called stimulated Raman scattering. And there is a huge zoo of effects. And I'll show one example in a minute. So Raman scattering, which means that a photon h bar omega is destroyed, yeah, and a photon at a Stokes shifted frequency is created. So let me just show a figure for that. I don't have a figure here, so I have to draw it myself. Okay, but this. So the idea is the following, that we kind of have, yeah, well, two ground states. You may one might say. So say two vibrational levels, and then what we would do is to drive a transition like depicted here. Yeah, so this here would be the Stokes shifted frequency h bar omega s is equal to h bar omega minus h bar omega v. Yeah? And well, there are coherent processes and there are incoherent processes. And an example for coherent processes is, well, actually in a spectacular form is what is shown here. So what Steve Harris and his group in Stanford, well, Alexei Sokolov was my colleague at Texas A&M University. So what they did was to use a cell with deuterium, filled with deuterium, and deuterium is of course a molecule, it has vibrational levels, so you can drive Stokes transitions, and this is what they actually do. So they use two lasers with frequencies that are just separated by the vibrational frequency. So I should show here this here. Yeah. So I start once again. So the experimental scheme is the following. So there is a deuterium cell, and deuterium is of course a molecule with a certain vibrational spacing. And then you use two lasers with frequencies corresponding, so the frequency difference corresponds to this vibrational level. And then one can drive such Raman transitions actually coherently. And actually you can drive them in a cascaded way. So you produce a new frequency, and this new frequency then mixes with the frequencies that are already there in order to produce again a new frequency, and you cascade this, and this gives a very colorful experiment as you see here, right? And the difference, so they are all separate, so the wavelength difference corresponds to the vibrational frequency, which is on the order, the period, the vibrational period is on the order of 10 femtoseconds. So 1 over 10 femtoseconds, this corresponds to the frequency spacing of these lines. Okay, but this, I think, should be enough for non-parametric processes, and we would go to the next chapter. As I announced, we want to derive the coupled wave equations, but before we do so, we open the windows for a few minutes, and I take the time and write down the headline of the next chapter. So in the script, this would be chapter 7, I guess, but we try to come as quickly as possible to the coupled wave equations. And we'll just summarize the content of the previous chapters. Well, one of the chapters, particularly on anharmonic oscillators, this will come later. But I think it's important to come as quick as possible to the coupled wave equations. So we have now chapter 3. Chapter 3. Maxwell's equations and nonlinear interactions. Maxwell's equations and nonlinear interactions. So, and we start with some general remarks. So the idea is kind of, well, when you want to derive something, then it's always a good idea, when you want to derive something, then it's always a good idea to know where it will go. Actually, there was a famous physicist who said, never start a derivation without knowing what comes out. Yeah? And so in the first subchapter, we'll think about what should come out. So I think this is enough for the moment. So 3.1, general remarks in a qualitative discussion. Yeah, so it's about getting an idea of what should come out. And a qualitative discussion. So we start again with linear optics. And for linear optics, the superposition principle holds. Right? So light waves don't interact with each other, and this also means that no new frequencies are generated. Right? So if you have two light waves that don't interact, then there's no point or no possibility to generate new frequencies. So let's write that down. For linear interactions, the superposition principle holds, which means that light doesn't interact with other light. Yeah, so different waves do not interact. And this means no new frequencies can be generated. This is, of course, different in nonlinear optics. Yeah? There we said that we need to talk about not only linear polarization but also nonlinear polarization, and we already indicated that it's the nonlinear polarization that is responsible for creating new frequencies. Yeah? So we get new waves, right? And this means that we need, and the headline says it already, that we need, or that we will use Maxwell's equation to describe it. Yeah? So if nonlinear polarization is created, new frequencies will be produced, and the corresponding waves are described by Maxwell's equations. Have to be described. By Maxwell's equations. Yeah? So this means, say for a second order process where we have three frequencies, that we have three waves. Yeah? So we would use 3 times a wave equation. Yeah? So let's write that down. For example, for second order process, we expect, or we will have, 3 wave equations. Yeah. So the next thing that's also obvious is that these three wave equations will interact with each other. After all, at the entrance phase of the nonlinear crystal, you just have two waves, right? Yeah, so you have the two incident waves, and you generate in the crystal the third wave, right? And it develops somehow. And it's actually our goal to determine how this new wave develops. Or if you think about second harmonic generation, I mentioned already that it is possible to convert virtually all the fundamental light into the second harmonic. Yeah, so this means that the second harmonic grows within the crystal, whereas the fundamental goes down. So apparently, these wave equations must be coupled. Yeah? So the waves interact. And this means that the wave equations describing them must be coupled. Yeah, so we expect wave equations, so you know second derivative with respect to time and second derivative with respect to a spatial coordinate. Yeah, 3 times such a partial differential equation. There will probably be an inhomogeneous part to it because you want to produce the wave, right? And in addition to that, they need to be coupled. Yeah? So that's what we have to expect, but we have to expect actually more. We have to expect that there's interference between all these 3 waves. Yeah? And this is the large subject of phase matching. You know, so let's just think a little bit about it, what happens. So we have interference between original and new frequencies. Yep. And this relates to phase matching. And we take a specific example, namely some frequency generation. I include here a small drawing, yeah, like this one here. Yeah, so suppose we have this kind of a crystal, right? And what happens inside this crystal is that we produce nonlinear polarization. So there are dipoles that oscillate. They oscillate, of course, with these 2 input frequencies, but they, due to the nonlinearity, they also oscillate with this new frequency omega 3, which is the sum of these 2 frequencies, right? So the oscillation of this dipole has a frequency component omega 3, right? And accordingly, this dipole will radiate in a dipole-like pattern. It will radiate a wave with the frequency omega 3, right? So let's write that up before we continue. To be specific, we consider some frequency generation with input fields omega 1 and omega 2. Yeah? Due to the nonlinear response, the excited dipoles will oscillate and radiate, and thus radiate not only at omega 1 and omega 2, but also at omega 3 equal omega 1 plus omega 2 for the case of some frequency generation. Yeah? And if we consider a single atom, then this oscillates like a dipole. Right? So this cosine square-like pattern. Yeah? An individual molecule or atom will radiate a dipole-like emission pattern. Yeah, would look something like this. Something like this here. Yeah. But we have, of course, not just one atom, we have many of them, and each of them radiates. Now, if they radiate in phase, then in a certain direction, yeah, so in the direction in which they radiate actually in phase, the emission will increase by the square of the number of oscillators. Yeah? And and then you don't have, then you have a much narrower emission characteristics. Yeah, so so many, or the emission of many, the emission of many particles will interfere and for constructive interference, the intensity would grow with the square of the particles that emit. The emission would grow with the square of dipoles. Yeah. Again, a quick drawing here. Yeah, so now you see that we have many of these dipoles, right? And if they emit in phase, then you would get, say, this emission characteristics. In the opposite direction, they typically interfere destructively. So if you have a laser beam that excites them, right, then this laser beam would come in from this side. It would first excite this, right, then excite this, then excite the next one. So they all have a phase difference for their emission. And so this one is excited later than this one here. But, so this was excited earlier, but if conditions are right, it will catch up just because of this difference, right? And now you see what happens. Yeah? So this one here is later excited. Yeah? This was excited earlier, so this emission starts earlier, but arrives just here when this here is excited. Right? So therefore you see how constructive interference works here, provided that the travel time of the light, from here to there, is the same than the light that's produced by this atom, so that the speed of light of both frequencies is the same. Right? So in the linear case, this is automatically given, because they only radiate at the frequency at which they are excited. However, if you have nonlinear polarization, or if you have if you have the nonlinear case, then of course the sum frequency, so the newly generated light, so the light at omega 3, has a higher frequency and therefore a higher refractive index if we speak about normal dispersion, right? So the blue light here produced by some frequency generation will arrive later here, right? And therefore the light generated from this dipole and from this dipole are not in phase. And now you have to make special tricks in order to kind of make sure that the speed of light for both frequencies is nevertheless the same. How could you do that? Well, imagine you have a birefringent crystal and the light that excites these dipoles oscillates perpendicular to the drawing plane and thus sees maybe a different refractive index than this one here, right? Then you can kind of, then you can match both phases. Yeah? And this is why it's called phase matching. But we'll come to that. Yeah, so, and phase matching, this needs to be part of these coupled wave equations. Yeah, so this is another thing that just by thinking about the problem, we can predict. Yeah? So our coupled wave equations, they must include phase matching. And they will, of course. So let's quickly write that down. The interference of the individual dipoles will be constructive when their oscillation or oscillations are excited in a synchronous way. So as just discussed. So dipoles sitting at coordinates sitting at coordinates sitting at positions with larger coordinate, coordinate z. Yeah, so the idea, it's depicted here actually. So this is beam direction is the z-axis. Yeah, so dipoles sitting at positions with larger coordinate z have to radiate such that the radiation we don't see the handwriting. Is this true? It should be there. Are there? Okay. This is a new question. Are there cases where the fields are such that also higher multiple order radiation for each emitter becomes relevant? Currently, we only assume each emitter is a dipole. So the question is whether there's quadrupole or octupole emission. I'm not aware of any of these. Yeah? So quadrupole and octupole. So now think of the following. We are talking about nonlinear effects, which are weak as compared to linear effects. Yeah? And now you ask about quadrupole transitions or even octupole transitions or something like that, and they are per se weaker than dipole transitions. So there are, I would say, two penalties in some sense. Actually, I'm not aware of such effects, not to speak of the uses for producing in a nonlinear way radiation. Okay, so let me continue this sentence here. Dipoles sitting at positions with larger coordinate z have to radiate such that the radiation of dipoles sitting at smaller coordinates or positions with smaller coordinate z, such that the radiations of dipoles sitting at smaller z is in phase. And this is called phase matching. Yeah. Yeah. And this is only possible, at least in most cases. This is with a grain of salt, cum grano salis, only possible if the input fields propagate with the same phase velocity. as the output fields. That details we'll see in, well, next time actually. Yeah, so once we have derived the coupled wave equations. As the output fields. Okay, so now we know what to expect, and now we can try to do the math. Yeah, so this is chapter 3.2. This is the wave equation for nonlinear optical media. So I think we opened the windows for a last time. Yeah, and we would start with what you did often in your career already, and also a couple of times already in this course. Namely, we would derive the wave equation. And how is it derived? Well, what you do is that you take the curl of Faraday's equation and you substitute Ampere's equation. Further, you make certain assumptions. Yeah? So you say we are in optics after all, so there are no free charges. So the charge density is equal to 0, and also there are no free currents. So J is also equal to 0. And in addition, you would say, well, the medium is non-magnetic, yeah, because otherwise we would have iron or something like that, which is also not transparent. So we make these usual assumptions and derive the wave equation in this way. Yeah, so we derive the wave equation in the usual way under the usual assumption. Yeah, so just as in chapter 1. Yeah, and what we get then would be that the curl of the E field is equal to minus mu naught times the second derivative of the D field. Yep, so I call this here equation 4. So that's enough fresh air. The next thing would be, remember what we are after. So we are after an inhomogeneous wave equation. So, and we know that the inhomogeneity must have to do with the polarization. So what is natural to do, if you know that, is to write the D field as a sum of the electric field and the polarization, right? So we use that the D field can be written as epsilon 0 times the E field plus the polarization, right? And in addition, we use the dispersion relation. Yeah, so mu naught is 1 over epsilon 0 times c squared. And if we do that, then we get that the curl of the E field is equal to minus 1 over epsilon 0 times c squared and the second derivative of epsilon 0 times E plus the polarization, of course. Yeah? And yeah, and then once again, what we want to have is So what we say is that the polarization later will take the nonlinear part of this polarization. We say that this creates the wave. So this is the inhomogeneity of the partial differential equation. So therefore, it's natural to move this here over there. So we get, therefore, that the curl of the E field plus 1 over c squared and the second derivative of the E field is equal to minus 1 over epsilon 0 times c squared, and then the second derivative of the polarization. So that's equation 5. Yeah. The next thing, just as in linear optics, we kind of want to say that the curl of the E field can be simplified, and we use the famous Buck-Cup rule. But then we have to argue that the gradient of the divergence is equal to 0. And in linear optics, this is fairly simple to argue, because what you say, at least for isotropic media, what you say, and this is the case in most parts of optics, isn't it? So if you have glass or something, this is always the case. So if you have isotropic media, then it's fairly simple to show that the gradient of the divergence of the E field is equal to 0. Now, in nonlinear optics, this is not the case, because the argument that you make is that you again that you start with Gauss' law, and you say that the divergence of the D field is equal to 0, right? And then you would write the D field as the sum of the E field and the polarization, and you say, well, if this sum, and then you write the polarization as susceptibility times the E field, and then you see that the divergence of the E field must also be 0. Well, in nonlinear optics, this doesn't work for 2 reasons, actually. Quite often, you don't use isotropic media. And the other point is that you can't write the polarization in this way. Yeah, so you can't write just that the D field is equal to the E field plus this linear part of the polarization. You would also have to include the nonlinear part. Okay, so the usual argument of linear optics doesn't work in order to simplify it here. Well, then there's another argument that you could apply. You could say, well, the wave, if the wave is a plane wave, right, then the divergence of the E field, of course, is 0. Unfortunately, if we make nonlinear optics, then we need high intensities, and this means that we focus our beams. So we are not precisely, we don't have precisely plane waves. Yeah? The bottom line is that we don't have good arguments to say that the divergence of the E field is equal to 0, but we have a good idea that it's small, right? And after all, we need to go on, right? And we need to make approximations. Yeah, so it's here an approximation, I have to confess. So we say that the divergence of the E field is sufficiently small. I lost a lot of words. We assume that is, yeah, that this is small, right? And then we can write this curl of the E field then this is equal to minus the Laplace operator times the E field, right? And with this, we arrive at Laplace operator of the E field minus 1 over c squared, then the second derivative of the E field with respect to time, that this here is equal to 1 over epsilon 0 times c squared times the second derivative of the polarization. Yeah, so you see, this looks already a little bit closer to what we want to find. Yeah? And now the next point would be to split the polarization in its linear part and in its nonlinear part, right? But unfortunately, time is up, so I have to I have to close here. But you see, we can conveniently continue at this point on next Monday. Yeah, so what we will do is to split this here in a linear part and in a nonlinear part. And the linear part we will bring to the other side, yeah, because this doesn't produce new frequencies. And then we'll have only the nonlinear part here. Yeah, and this will be another 90 minutes of mass, and then we'll hopefully arrive at the coupled wave equations in the next lecture. So there's a question here: does the small divergence come at a cost? Because in most experimental setup that I know, the nonlinear crystal is bumped by a focused beam. Yeah, so this is what I said. Yeah. It depends now on how strongly it is focused. Yeah, so usually the approximation of a plane wave is still not a bad approximation. But if you would ask me whether I would be able to quantify the deviations from what we calculate, then I would say no, I have no experience in that. Yeah. So when you ask, does it come at a cost? Yeah. So sure. Yeah. So what we calculate will not be exactly what nature is doing, right? But this is the usual case in physics, that we make approximations, and then it depends on how good the approximations are and which accuracy we need. So with this, I would like to thank you for your attention and see you next week again. Thank you. More questions? Will this approximation break down for strong self-focusing, since in this case the divergence could get really high or not? Well, maybe this is a question that needs a little bit more consideration, because, well, if we speak about self-focusing, then actually you come quickly to the situation where there are counteracting effects. Yeah? So if you induce self-focusing, say, in air or in a crystal, then you will quickly arrive at a situation where the intensity is so high that the material is ionized. And what happens then is, well, that the focusing effect is counteracted by the free electrons. Yeah? So you don't you don't focus harder to do self-focusing. Actually, if you really want to force this situation, if you really want to let break down this the situation where a plane wave is a bad approximation, then what I would recommend to you would be to use a fast lens. Yeah, so a lens with a low f number. You will not be able to focus harder by self-focusing. And then you could, of course, ask, what happens in nonlinear optics if I do this? Yeah, if I focus so hard and want to produce maybe second harmonic generation. Yeah? The result will be, so the answer is that the efficiency will not be very high. Yeah? For different reasons, actually. Right? So if you want to produce a high efficiency for nonlinear effects, say in a crystal, then you better try to focus not too hard. Right? Okay, with this we really close. Thank you.